As it was indicated, the title of my talk is dealing with the low power consuming time-interleaved all-optical ADCs at the rate of 160 gigasamples per second. And the effective number of bits that we are targeting for is 10 effective number of bits. So we would be able to use that for a variety of applications that are related to the future telecommunication system, remote sensing and radar systems, as well as the test equipment and instrumentation. This is the work that it's the effort of my students in my group, and I wanted to specifically thank Dr. Xiaobo Ho, Dr. Li Zhang, Dr. Masani Sahajulum, Dr. Tianqi San, and Dr. Kai Wei. And we are all from Drexel University, and the work has been sponsored by Synergy Microwave Corporations in Paterson, New Jersey. And specifically, I'd like to thank the generous and continuous support of Professor Ulrich Rode and also Professor A.J. Kumar. The outline of my talk is presented in this slide, which I will start up with the background of analog to digital converters. And then I would focus on the optical ADC design. And then I would focus on the single chip design aspect and the challenges associated with that. The challenge that we have been focusing in is a challenge that has been posed by DARPA in 1990s, where to provide a fully interconnected low Earth orbit, as well as the medium and geosynchronous orbit, to a variety of flyers that are going to be on airborne, as well as the land-based and ship-based structures. And this challenging problem is quite suitable for a variety of applications that are related to the remote sensing and telecommunications as well. In particular, as it is shown in the block diagram, you're going to have a phased array antenna, and you can take advantage of the copole and cross-pole antenna structures and take the information in a polar format and input to the all-optical ADC using a direct digital conversion. And you will take the information in M bits, and then you would be able to perform sophisticated field programmable gate array signal processing functions of FFT, angle of arrival estimation, and digital beamforming network. And the goal is to be able to have a very broadband system. And let me share with you one aspect which is related to the V-band satellite system operating around 50 gigahertz. And if we consider a typical 10% bandwidth system, you're looking at a minimum bandwidth of about 5 gigahertz. And if we use the Nyquist sampling, you have a 10 gigasamples per second for that 5 gigahertz of bandwidth. And then we require a minimum of 8 bits, which imposes a very high signal to noise ratio of 50 dB. And the 80 gigabits per second of data, now it's going to be encoded using the 8B, 10B encoding scheme. So you end up with a data of 100 gigabits per second per radiating element. And if we have as many as 128 receivers, then you can simultaneously generate as many as 128 beams. And the data throughput associated with that is going to be larger than 12 terabits per second. And the electronic system has to operate at 100 gigabits per second. And this is a very challenging capability, which is imposing power consumption issues. In particular, in a harsh space environment, you are going to have many challenges in terms of the heat removal, and it is going to be very costly. And as a result of it, you have to come up with the design topologies that are going to be low power consuming as well as the high speed. So let me give you a little bit brief overview of what analog to digital converters, in particular, the holy grail of the direct digital receiver configuration. So let's say that the incoming signal in the radio frequencies is being detected by a antenna, and then after the front end processing of boosting the signal using a low noise amplifier, you're going to take that RF signal to be sampled by a high speed as well as the high stability clock signal. And then you take the sample information and you quantize that using a quantizer with the M effective number of bits. And that M bits is going to be given to the signal processing function to be able to do the number of mathematical functions. If we look at a ramp signal as it is indicated in this graph, you can quantize that as it is shown in here with the 16 different levels. You would end up with a quantization error, which is the difference between the analog information and the digitized version of it. And naturally, we wanted to minimize the quantization error to have the signal in a digital format as close as possible to the analog information. And if you're looking at the information that is going to be sampled, the least sampling rate that you have is a Nyquist sampling, and you wanted to have the sampling that is going to be faster than the Nyquist in many applications, such as the Delta Sigma ADCs. The other electrical-based ADCs are based on the flash or pipeline. However, these electrical ADCs at the rate of 40 gigasamples per second, which is the minimum requirement for the 20 gigahertz of bandwidth, you are going to suffer the electrical aperture jitter, which is a problem in terms of the number of bits that you can have. The solution is to use the optical sampling techniques where you're going to have a lowest aperture jitter available, and then do the quantization, whether it is going to be in electronic domain as it is advocated by various groups, or it will be all in the optical domain as it has been advocated by my group and few other institutions. The key aspect is you need to have a effective number of bits to be a minimum of 8 bits, which requires a 50 dB signal to noise ratio at a very high speed that are dealing with the 40 gigasamples per second. The challenge that you're going to see is when you increase the sampling rate to 10 and above, you're going to have the challenge of the power consumption and also the fact that you would not have the high resolution. And the talk that I'm making today is to clarify how we are going to accomplish this. One of the challenges that we are dealing with is the challenge associated with the thermal aspect of the electronic circuits, as well as the bandwidth of the electronic circuits that are manifested in thermal and ambiguity, and then the quantum limit of the Heisenberg. But as you see in the blue curves, the limitation that you're going to observe is the aperture jitter. And if you're going to have a very low aperture jitter of 0.2 picosecond, then you have a hope to reach a 10 gigasamples per second with a minimum of 8 effective number of bits. But our goal is 10 effective number of bits. And as you will see in this graph, the timing jitter requires for a 10 effective number of bits is going to be at the rate of about 20 femtoseconds. So in this respect, when we look at the equivalent number of bits versus the aperture jitter, you observe that for a information that it is 200 megahertz of bandwidth, that gives us the 400 megasamples per second. With 100 femtosecond, you can achieve as many as 12 effective number of bits. However, when you look at the 40 gigasamples per second for a 20 gigahertz of bandwidth, then you end up with only 6 effective number of bits if you're going to have 100 femtosecond. So you have to push that to the lower aperture jitter. In electronics and RF domain, we usually talk about the aperture jitter in terms of the close into the carrier phase noise. And you will see that for the 400 megasamples per second, the clock of 200 megahertz, or in red for the 40 gigasamples per second, the clock of the 20 gigahertz is required. And as a result of it, when we look at the 100 femtosecond aperture jitter, the close into the carrier phase noise has to be lower than minus 110 dBc per hertz. And that is a challenge in terms of the electronic circuitry. And the challenge comes from the fact that the feedback circuitry, the bandpass resonator, has to have a very high quality factor or very high selectivity. And in fact, the close into the carrier phase noise, which is directly related to the aperture jitter, is going to be inversely proportional to the quality factor squared. So in essence, if you increase the quality factor by a factor of 10 or 1 decade, then what you're going to see is a 20 dB reduction in the close into the carrier phase noise. Electronic as well as the optoelectronic oscillators has been compared in this tabular representation. And as you see, the optoelectronic oscillators gives us the frequency well into millimeter wave frequency range of about 100 gigahertz. And you would be able to have for 10 gigahertz frequency a Q factor that it is about 1 million, which leads to a close into the carrier phase noise of minus 140 dBc per hertz at 10 kilohertz offset. So that's a typical behavior which gives us the advantage of having a clock in an optical domain. And since our clock is going to be in the optical domain, then let's see what are the possibilities in terms of the sampling and quantization in optical domain. And I would discuss the topologies that are available. And in particular, I focus on the approach that has been advocated by my group, which is the spatial light modulator, and in particular, improving the performance with the photonic crystal structures. Professor Henry Taylor in 1975 introduced a design of an all-optical ADC based on a mode lock laser for the sampling to give a high frequency stability, and then using a Mach-Zehnder interferometer to achieve the quantization process that you would have in this respect. So you're going to take the incoming RF signal and apply with the electrode of delta L in length. And then the next electrode is going to have a 2 delta L, 4 delta L, and 8 delta L for the 4 bits. And if you're going to have for m bits, you need to have the lengths that are going to be 2 to the power of m minus 1 times delta L. And as a result of it, what you're going to experience is for a length that is going to increase significantly. For example, for 10 bit, you're looking at almost about a 900 times delta L. The difference in the velocity of the radio frequency signal that it's traveling along the electrode minus the speed associated with the optical wave that it is traveling also along these electrodes in the optical waveguide will limit the bandwidth. Therefore, this is a major problem that you're going to have a bandwidth limitation very early on, and you cannot achieve more than a few bits of resolution. To resolve this matter, the ingenuity of the time and wavelength interweaving has been used, and you will see that the RF signal in the form of a sinusoidal signal modulates optical energy that is coming in the form of the pulses, and you will see the envelope of it is shown in here for the short optical pulses that are coming in. To quantize that, the approach that has been used is a hybrid approach where you're going to take an optical switch and you're going to switch it at certain rate that are related to each individual pulses that are coming in. Then take that optical information and you're going to detect it by a photodetector, and then you digitize it using the electrical ADC. And then you need to very accurately stitch back the information to generate the same kind of pattern. Unfortunately, this is a very complex process, and it has a lot of problem in terms of the accuracy of the amplitude and time alignments. And as a result of it, is not very practical. The approach that I have advocated since mid-2000 is the approach to use the spatial light modulator as opposed to the amplitude modulation. And in this case, we are going to take the RF signal and cause the deflection of the optical beam in an angular fashion. So you're going to convert RF energy to the angular rotation. And this angular rotation of the fixed amount of light is going to hit the apertures. And in this case, I'm showing the optical apertures that are for the 4 bits of resolution. And you can imagine that we can increase the number of optical apertures to as many as 10, or rather than having a binary code, you can also make that in a form of the gray code. The key aspect is to make sure that the electro-optic deflector has an improved sensitivity. But we can also quantify the fact that there is 2 parts of the system. One is the spatial samplers portion, which includes the clock signal as well as the electro-optic spatial deflector. And then you are going to have a quantizer. And let's look at each one of them individually. For example, when we are looking at the phased array antennas and the signal is coming into an individual optical ADC, what you're going to get out is the M bits that is going to go to the processor. And the way that we are going to accomplish that is using the 2 parallel electrodes that are coupled microstrip line, and then the optical energy travels between these 2 electrodes. And if the velocity of light and the velocity of the RF signal are the same, by taking advantage of an appropriate substrate such as silicon, we would be able to have a very broad bandwidth capability. And the optical energy as it travels, because of the superstrate with the higher index of refraction, it causes the energy to be leaking out. And that leaky wave is going to have a diffraction pattern that is going to be narrow based on the length of this leaky waveguide structure. And we would be able to see the angular deflection, which is represented by this angle of theta r at the exit. And then based on the resolution, we would be able to achieve a large effective number of bits. In fact, we have been able to demonstrate a 40 gigasamples per second with the 6 effective number of bits. And you will be able to observe that also the quantization levels that are indicated in here in that respect using the quantizer. But our goal is to achieve a higher effective number of bits. And let's see what are the compromises that you have to make and what kind of innovation you have to introduce. So you will see the simulated performance using the optical FTTD, and it shows the energy that it is traveling through the optical waveguide. And the optical waveguide, as you see, the energy is going to leak out, and the angle of the leakage is given by theta leak. And the leakage condition is satisfied by making sure that the index of refraction of the prism, which is given by 1.7, is higher than the effective index of refraction of the optical waveguide, which is tunable by the electro-optic property of the Pockels effect due to the applied RF field. There is a very thin layer of the buffer layer which controls the leaky wave coefficient, which controls what is the angle of the delta theta, which is a diffraction angle. And as you see, the theta leak that we have for the N effective, which is now controlled by the applied electric RF signal, is going to be adjusted. and as a result of it, you're going to have a deflection angle. So let's see how does it appear. And as you see in this animation, the light is being deflected at different angle as we apply a different applied RF field. So the approach that we are using a very short optical pulses using a clocks that are highly stable. The RF signal is being provided with the spatial light modulator, and then the deflected beam is impinging on the coding mask, where behind the coding mask we have a very high speed photodiodes constructed. And since the optical energy is going to be the same, what we are going to have is a high signal to noise ratio, which is advantageous over the other structures. Our goal is also to take this design topology and make it an integrated version. And the steps into integrated version is next items that I will be discussing. But in terms of the perspective, let's look at the hybrid ADC, where you're going to take advantage of the sampling in optical domain, and then you're going to do the quantization in electronic domain. And as you see, there is a limitation in terms of the speed or the effective number of bits. And then if you do an all-optical, if you do the MZM base as it was presented by Professor Henry Taylor, you end up with the 1 gigasamples per second as a maximum speed with a 6 effective number of bits. And then you would be able to have also a tunable laser-based system, which gives us only a 4 effective number of bits. And there has been another methodology, which is based on a photonic crystal, which gives a very high speed, 52 gigasamples per second, but the effective number of bits is limited to 2. My team, Dr. Shabo Ho in 2005 and Dr. Hajilum, they demonstrated the 40 gigasamples per second with the 6 effective number of bits. And what we have done is we have taken those approaches and we have modified that by using the slow light effect. The slow light effect is based on a dispersive characteristic of the index of refraction with the operating frequency. So rather than being in a TEM mode of the propagation, you would have a non-TEM mode, and you're going to have a dispersive characteristic due to the periodic structures of the slow light wave structures. And there has been use for a number of applications, including the delay line. So our approach has been to improve the performance of the spatial light modulator by adding the 1D photonic crystal. And the 1D photonic crystal is grown on top of the electro-optic polymer with the separation of the buffer layer. And then on top of the 1D photonic crystal, we place the prism. And the prism is going to have the light that it is deflected, and then it's going to focus that using a cylindrical lens on a coding mask. And the key aspect is we wanted to have the sampling using a very low jitter clocks. And then we wanted to have also very efficient light modulators based on the photonic crystal, and the issue of the optical quantizers we have already addressed. Let's see the design that we need to go through for the 1D photonic crystal realization. And it's a periodic structure with the periodicity of A. And if we adjust that from 410 nanometer all the way to 550 nanometer, and I have highlighted the 3 of these plots. One is for the 410 nanometer, which is in the photonic band gap engineering, where you're going to have a lot of attenuation. And then for the 500 nanometer, with the fill factor of 60%, you would have a photonic crystal domain where you're going to have a dispersive characteristic, and the group index is going to be increasing. And then you're going to have in the light cone region, where you have a linear characteristic, and the group index as well as the phase velocity index, they are equal to one another. So the dispersive characteristic is going to be at 1550 nanometer of the optical energy, which is related to the telecom application sources, and is going to be in the photonic crystal domain. And you observe that the attenuation that you're going to experience based on the leakage of the wave is also simulated in here. And the key aspect is the light energy now is going to leak out through the photonic crystal structure, and then it's going to reach the prism, and then from a cylindrical lens is going to be impinging on the optical aperture. And the effective number of bits is going to be given by the total swing of the angle due to the voltage applied to the electrodes of the traveling wave structure, is going to give us a maximum of a delta theta, and the diffraction angle is going to be the lowercase of the delta theta, and then the log in a base 2 of this quantity will identify what the effective number of bits is going to be. Note that with the electro-optic material, R33 is going to be adjusted with the applied electric field, and as a result of it, the angle at the output is going to be controlled. So we have optimized these designs, and we have used the CPO1 chromophores in the PMMI host material, where we end up with the 136 picometer per volt as an effective R33. And as a result of it, we end up with a 7.5 effective number of bits. And you see the diffraction angle delta theta, and the zoom in feature of it is shown in here, as well as a total swing that you're going to see between a positive and negative applied voltages. So now the next issue is how we can achieve this design in a single chip design to make it not only very robust in the harsh military or the space environment, but also take advantage of the lower cost and more cost-effective implementation. So for the very stable clock signal, we use the self-force multimode laser as an optoelectronic oscillator to generate the clock signal, and then we use a time interleaving using the 2D photonic crystal add-drop filter to be able to achieve the 160 gigasamples per second. So let me talk about the small size clock that we have developed using the indium phosphide-based laser implementation by taking advantage of the gain medium using the semiconductor optical amplifier, a phase modulation section to adjust the time delay through the cavity, and then building the cavity using the DBR, distributed Bragg reflectors, in the front as well as in the back. And what we have done is two identical lasers that are sharing the same back DBR section. And as a result of it, we can create a large number of modes as the total length of the cavity is large. And based on the length of the cavity, then you have the intermodal frequency that are being generated. And these intermodal frequencies, they can be easily tuned with the phase section modulation. And the number of modes that will appear in the system can be also controlled by the amplitude modulation that is based on the quantum confined Stark effect as an electroabsorption modulator. So here is the microphotograph of the chip in the indium phosphide, and you will see the SOA, which is the semiconductor optical amplifier, the phase modulator section. And as you see that there is a symmetry between them, and you have the electroabsorption modulator and the DBR in the front and the shared DBR section. And you can see the performance of this compact multimode laser where we have used the self-injection locking to achieve a close into the carrier phase noise of -85 dBc per hertz, or do a self-mode locking to achieve -100 dBc per hertz, or combination of both, which gave us the -110 dBc per hertz, as I had identified as a minimum requirement that we have for the clock. And the key aspect is these technologies are compared to the modular designs, and you see that the modular design has a better performance because of the fact that you can achieve a longer delay system. We can increase the number of modes in the semiconductor laser as a multi-mode laser, and moving from 5 modes to as many as 125 modes, you end up with the timing jitter less than 2 femtosecond, which gives us about minus 142 dBc per hertz in terms of the 10 kilohertz offset carrier. Now, the next step is to achieve the delays using the add-drop filters. And add-drop filters are based on the microdisc resonators, and the optical energy enters in here. And if it matches up with the resonance of this structure, then the energy could leak out through the drop port. If it doesn't match up with the resonance, then it goes through the through port. Analytically, you can show that by a transfer function and look at the delay in terms of the insertion phase, and in particular, the derivative of phase with respect to frequency. And you need to also recognize that you need to have the free spectral range to be controlled to match up with the modes of the multi-mode laser. And to make the design smaller in size, we took advantage of the 2D photonic crystal add-drop filter with the periodicity of 500 nanometer and a fill factor of 17%. And it's everything constructed based on silicon. And you can see when the wavelength doesn't match up with the resonator wavelength as a resonance frequency, then the energy goes through the through port. However, when it matches up, the energy is going to be coupled through the drop port. And we take advantage of the scatterers that are strategically located to make the attenuation as low as possible. And if we use the structure of the add-drop filter in a cascaded manner, using the radius of 4.36 millimeter, you would end up with a delay that it is around a microsecond. However, using a 2D photonic crystal structure, then the selectivity is much better. And look, I'm here zooming in a very narrow region, and I'm also using only 100 micrometer in radius, and I still achieve a delay that it is in a range of a microsecond. And the chip size is about 5.6 millimeters squared versus the chip size of the 27 centimeters squared. And this is the construction of the clock signal where the multi-mode laser based on the indium phosphide is heterogeneously integrated on a silicon substrate. And we have the realization of the delay using the add-drop filters, and with 2 different time delay of tau2 and tau1 for the self-electrical injection locking and self-phase locking, where the instantaneous RF frequency and RF phase are being compared against the delayed version. And any differences are going to be corrected for using the phase lock loop as well as the self-injection process. And when you look at the improvements that you're going to have in terms of the ADC based on the all-optical ADC with and without the photonic crystal, circa of 2016 in my group and circa of 2020. And you see that we have improved from the 6 effective number of bits to 8 with the 40 gigasamples per second. And compared to the other methodologies, not only in terms of the sampling rate, we are better, but also in terms of the effective number of bits. Now, when we put everything together, which is the clock signal as well as the spatial light modulator and the coding mask, which is going to be in free space optics, and the antenna that it is a Vivaldi antenna that it is being placed also on a silicon substrate. And you're going to have the chip that is going to be about a 3 centimeter by 4 centimeter. And this chip is going to have the capability using the CPO1 with the 40 gigasamples per second, power consumption of 200 milliwatt with the effective number of 7.9. The new chromophore that we are employing, JRD1, gives us the higher effective R33, and that brings the effective number of bits to 9.4 with a power consumption of about 230 milliwatt. And this design has a lot of advantages. And one of the advantages that we have is the low power consumption can be now integrated as a interleaved structure. And since everything is integrated, the multimode laser is going to be split in 4 paths. One path doesn't have any delay. The path number 2 is going to have a delay of tau 0, which is equal to 6.25 picosecond. The path number 3 is going to have a time delay of 2 tau 0, and the path number 4 is going to have 3 tau 0. And each one of these are going to be receiving the in-phase RF signal. And what will happen is, based on the sampling time that you have, the information is going to be sampled. And now you're going to have the information added together in the optical domain, and you're going to have the interleaved information very accurately, because everything is in our chip level, and you're going to have a absolutely highly accurate configuration. And you can see, based on the data, you would have under a 1 watt of the power consumption for each one of these 4 interleaved structure, and you have about 9.5 effective number of bits, and you do have the capability of 160 gigasamples per second effectively. So in conclusion, I wanted to share with you the vision that we have and put that in perspective with respect to the other technologies that are available. The optical time and wavelength interleaving, which was demonstrated at NRL, 10 gigasamples per second, 100 milliwatt only for the optical domain, and it doesn't include the clock information, and it has the maximum of 7 effective number of bits. The electronic domain, using the very high speed IBM chips, they did it 48 times time interleaved to achieve 32 gigasamples per second with the power consumption of about 200 milliwatt and the 10 effective number of bits. But with the all-optical technique, we have a very reasonable power consumption of under 1 watt and speed of 160 gigasamples per second with the approximately 10 effective number of bits. Thank you for your attention. And if you have any questions, don't hesitate to reach out to me by my email, and I would be glad to entertain any questions that you have right now as well.